Hi kids, it's Mrs. Geiger here. So today I'm going to talk about something known as the ideal gas equation. So, first I'm going to go back and talk about what the difference between an ideal gas and a real gas is. But I'm going to jump back to this screen. So this is what's going to be coming next. So if you haven't already taken out your notebook, I'd like you to do that, please. And so we're going to be talking about ideal gases. Now, ideal gases are just a model. So this is the idea. In order for us to be able to use the combined gas law, we need to make some assumptions about gases. Now, we've been talking about gases since literally the beginning of the year, and when we talk about gases, we always say that the particles are in constant random straight line motion and that they do not have intermolecular forces between them. So then later in the year, we learn that van der Waals forces exist in all substances that have mass. So that means that gases do have intermolecular forces, but they are so weak that we don't need to account for those forces when we are looking at most gases. So we make this model. We take gases and we say, well, what if they were ideal? What if they didn't have any intermolecular forces between them? And if we do that, really the math works out and our calculations work out that we can use this model almost all the time without any issues. So ideal gases are a model for gases. And in this model, we say that they have a very large volume. Now, why do they have a very large volume? The particles are very, very spread apart. And so this would occur under conditions of high temperature and low pressure. So think about this, a large volume. Large volume would occur when the temperature is very high and when the pressure is very low. So real gases act most like ideal gases when they are under conditions of high temperature and low pressure. And that is because we are neglecting the intermolecular forces. Think about how we learned about atoms and the electron cloud model. That means that when atoms are hitting into each other, when they're colliding with each other, they're going to change shape a little bit as those electron clouds overlap. And when the nuclei get close enough, they'll repel and bounce off. Kinetic molecular theory does not think about atoms as having electron clouds, but instead simplifies them into the billiard ball model. So if we go back in time and think about what John Dalton knew about atoms and said atoms were indivisible, and he said that they act like billiard balls and they bounce off of each other. That hard sphere model is when, in that time period, is when all of these gas laws were created. So, ideal gases, we're going to neglect those intermolecular forces. But remember, it's just a model. Real gases are every gas that exists on our planet and our universe, really. And real gases have mass and therefore have intermolecular forces due to that mass. And some of them even are polar, and that polarity might cause those gases to stick together. But when we talk about ideal gases, we neglect all of those intermolecular forces. And instead, we say, well, those forces are so weak that we don't need to worry about them, and our calculations will still work out to be useful. So very important is that ideal gases, real gases act like ideal gases under conditions of high temperature and low pressure, and that is because ideal gases have a very large volume. All right, so now that you know about the theory of ideal gases, let's look at how we can do some calculations based on ideal gases. Okay, so what we learned when we looked at the combined gas law is that if we take the pressure in situation 1 and the volume and we divide it by the temperature, that's always going to be equal to some constant. And remember, we use the symbol K to represent a constant. So what is that constant? It turns out that we also looked at Avogadro's law, and Avogadro's law said that the volume divided by the number of moles was also equal to some constant. So through all of this, we figured out that we can actually, just like how in the combined gas law, you can have different factors changing, we could take a novel situation, a situation where it's not changing from one situation to another, and calculate the other parameters, knowing a few things. So if we know the pressure, and we know the volume, and we know the temperature, we can figure out the number of moles. But we need to take into account this idea of the constant. So we figured out that there was this gas constant, and the gas constant happens to be 0.0821 liters times ATM divided by moles divided by kelvins. So this gas constant is all about unit analysis. Because we're using pressure in ATM, which is calibrated off the fact that at sea level, we are at 1 ATM. And we're using volume in liters, and we're using moles. This constant just allows us to use all of these different units, and it's basically a way for us to do these calculations, and it kind of like syncs the units together. So I'll show you what I mean by that. If I was to solve this equation for R, which is that constant, I would have that the pressure times the volume divided by the number of moles divided by the temperature would be equal to that gas constant R. So our unit of liters times ATMs comes from our numerator here, where we have ATM times liters for our units, and then look at our denominator. Our denominator is in moles times Kelvin. So we call this a proportionality constant. It's a constant that allows us to compare different units to each other, and it allows us to take a look at this equation here for gases and know what that constant is always going to be. So what I would like you to do is determine the volume of 1 mole of a gas at STP, at standard temperature and pressure. All right, so I've made my list, and since it's pressure times volume is equal to the number of moles times our gas constant times the temperature, I wrote them in order. P times V is equal to N times R times T. So let's think about this. We're at standard temperature and pressure. Now, when we look on our reference tables, when we look on table A at our STP constants, we can see that we have two different types of pressure. We have pressure in ATM and we have pressure in kilopascal. For this question, we're going to have to choose our pressure in ATM. And that's because this gas constant has the unit of ATM. So these are all of the units we're going to use. So our pressure is going to be, you got it, 1 ATM. Volume is my unknown there. My number of moles is going to be, say, 1 mole. All right. My gas constant there is 0.0821 liters times ATM divided by moles times Kelvin. And my temperature at STP, remember it has to be in Kelvin, is going to be 273 Kelvin. So go ahead and solve for V here. All right, so you should have gotten 22.4 liters. So remember how we talked about that? It is 22.4 liters for 1 mole of any gas at standard temperature and pressure. So you should have seen this already. That 22.4 liters actually, if you ever forget the number, you don't need to memorize it as long as you have the gas law constant memorized, 0.0821 liters times ATM per mole Kelvin. But you should know that that's where this number 22.4 liters comes from. All right, so I want you to know that this equation, this ideal gas equation, is not on the Regents exam. That is honors material, but the concept of an ideal gas is on the Regents exam, and that concept will be tested. So you're going to have some homeworks related to this. The ones that are have questions about the theory of ideal gases are Regents level questions. But the questions that have calculations based on ideal gases, that is honors material. So this PV equals nRT does not appear in your reference tables, and that's because it is not on the Regents. So any question that I give you on this, I will also always give you this gas constant. I don't expect you to memorize that gas constant. Oh, but I do want you to know that the gas constant comes in a few different varieties, and that's because the units can be different. And when the units are different, that means that the value here is different. All right, so that's it on ideal gases and the ideal gas equation. All right, hope this was helpful.